presenting the Carnot cycle. The Carnot cycle is a theoretical reversible cycle that utilizes four processes that are depicted on our PV and TS diagrams. Of the four processes, there are two adiabatic processes and two isothermal processes, as depicted here and here. An adiabatic process is a process in which there is no net entropy change, and an isothermal process is a process in which there is no net temperature change. In the process going from state 1 to state 2, we have an adiabatic compression, where work is being done on the gas and where there is no net entropy change. In the process going from state 2 to state 3, we have an isothermal expansion, where the gas is doing work on its surroundings, where it is remaining at a constant temperature, TH, and where it has a net heat transfer from the hot temperature reservoir. In the process going from state 3 to state 4, we have an adiabatic expansion, where it again is doing work on its surroundings and where there is no net entropy change. And lastly, we have the process going from state 4 to state 1, in which there is a net amount of work being done on the gas, where the gas is remaining at a constant temperature Tc, and where the gas is rejecting heat into the cold temperature reservoir. As we currently have the cycle depicted here, we have arrows going in a clockwise fashion. In this current way that is depicted, the cycle would be a power cycle, where the gas is doing a net amount of work on its surroundings, which would make sense if you were to depict the positive work done by the gas as the area underneath these two curves here, and the work being done on the gas as the area underneath these two curves here, where the net total amount of work is the area inside the area enclosed by the lines. If you were to reverse the directions of the arrows on this diagram, instead of having a power cycle, you would have a refrigerator or a heat pump, where there's actually a net amount of work being done on the cycle.
Now we're going to be discussing some equations that govern the Carnot cycle. For any cycle, the effectiveness or the efficiency of a power cycle and coefficient performance of heat pumps and refrigerators can be interpreted as the useful output divided by the input. For a power cycle, the thermal efficiency is given by QH minus QC divided by QH. For refrigeration heat pumps, the same sentiment applies, except that a coefficient of performance is analogous to efficiency. These are given by QC divided by QH minus QC and QH divided by QH minus QC respectively. For each of these equations, QH minus QC is equal to the work in the cycle. Now, for any internally reversible process, as in the Carnot cycle, we know that QC divided by QH is equal to TC divided by TH. This is because the ratio of heat transfers, QC divided by QH, depends only upon the temperatures of the reservoirs between them. By applying this equation to general efficiency equations, we see that the Carnot efficiency and coefficient performance equations come out to these depicted here on the whiteboard. Now, as previously mentioned, the Carnot cycle provides the maximum efficiency between two temperature reservoirs. This can be proven on the PV diagram. We know that the efficiency is the network of the cycle divided by the heat input. The network of the cycle is modeled as area enclosed by the process lines on the PV diagram. Now, it stands to reason that the more network, or the more enclosed area, the more efficient the process will be. By geometry, we know that the maximum enclosed area is given by a rectangle. However, if we draw a rectangle on our process lines defined here, we see that we are actually modeling two separate temperature reservoirs that are further apart than those of the previous cycle. Our TH is here, but it would come up here if we draw a rectangle, and our TC would come down here. Now, if we draw the accompanying adiabatic process lines from those temperature reservoirs, we do enclose, in fact, a greater area, which does more work, and we see that it does indeed model the maximum efficiency. In summation, the Carnot cycle is an internally reversible process that models a maximum efficiency between two temperature reservoirs, consisting of two adiabatic and two isothermal processes. Its efficiency and coefficient of performance are evaluated like any other cycle, but with the temperatures of both reservoirs used instead of heat inputs and outputs.